Okay, good morning everybody, and have a happy new year. Welcome to the first session this year. So let's continue where we stopped last time. So last time we started to look at warping filters. So we saw that warping filters can be useful for obtaining filters which have more detail, for instance in the low frequency region than in the high frequency region. And in this way, it gives a characteristic similar, for instance, to what the ear is doing. And this is the example that we had. So here we have a filter, and we replace the delay elements by all-pass filters. And those all-pass filters are now doing the warping for the filter. And for that, we designed the filter in the warp domain and got new coefficients, the C's here, which we designed for the warped domain. Right, so we had our requirements, we have the pass band of the low pass filter, and given this pass band and stop band, we designed the filter, but we did the design in the warp domain. And then we basically replace delays by those all-pass filters which do the warping to get our final filter. And here you can see the Python example for it. So you can see our all-pass filter. So here, this A we got from this formula last time for approximating the Bark scale. So this came out of this formula. We have an A and a B, which basically both together make up the all-pass filter for the denominator and the numerator. Then we have the input of our warped filter, which in this case is just an impulse, a 1 followed by 80 zeros, or 79 zeros, because we set the first one to 1 here. And then we take this as an input, and here's our warped filter. So here we can see that we need to compute the 3 different all-pass filters in our cascade of our filter. Here's the first all-pass filter, input is the impulse, output of the first all-pass filter, then the first all-pass filter output is input into the next all-pass filter, and so on into the third one. So we get 3 all-pass filter inversions here, and then we apply our filter to those all-pass filtered versions and the original version. So here you can see it. Here's the input without delay or all-pass filter, and here are the outputs from the all-pass filters weighted by our filter coefficients. And then the sum of them is the output, the final output of our filter. And then we can just analyze it. So this is the impulse response. So the FFT, the Fourier transform of the impulse response is the frequency response, which we can then see here. And here we can now see that we indeed have a useful filter. We have a pass band here, right? And indeed it's quite a narrow pass band. And we have a stop band, which has about maybe 30 dB attenuation. So it's not great, but it's not too bad either. Right? So remember, this is much better than the original design in the non-warp domain. In the non-warp domain, we basically had no pass band. It was all attenuated pretty much the same. Right? But here now we have indeed a functional low-pass filter with a very narrow band pass band. So this shows that it actually works. Right? And you can also take a look at the phase, and you can see the phase is very non-linear here. So this is unlike the non-warp version. For the non-warp version, we had a useless filter, but it had a linear phase. Right? So for the non-warp, we had a linear phase, which means all frequencies get the same delay. Here it's very non-linear. Yeah, so this is what I just said. So we get about 30 dB stop attenuation and a very narrow pass band from 0 to about 0.05 pi. So this is what we wanted to have. And we see that with warping we can do it. So now we can also plot the impulse response directly, which you can see here. So here we plot y out, and this is what we get. And now we can also see why we have a better filter now. And this is because we have a much longer impulse response. And so now we can see we have easily 80 significant coefficients of the impulse response. So that's much more than the 4 coefficients that we had in the non-warp version. Right. So this is what makes it work. And this is because now we basically have an IIR filter. So we started with an FIR filter for the design, but since we replaced all the delay elements by all-pass filters, and those all-pass filters are IIR filters, the resulting filter is also an IIR filter, infinite impulse response. Right. So this is what we see. We indeed have an infinite impulse response. So in principle, this actually continues infinitely long. It's just the most significant values that you can see here. Yeah. Right. So here, some references. Here is the paper where you can see the formula for the A coefficient. And here is one of our papers where we actually used warping to obtain a low delay audio encoder. Yeah, so does it make sense so far, warping? You think you could build filters, warp filters? Oh, okay. So then the next topic is minimum phase filters. So we already saw in the warp case that we have a nonlinear phase, and this is also what we will see in minimum phase filters. It's also different from the case of linear phase. So we know for the linear phase we have a linear function for the phase. So this phi of omega is minus omega times d, with some constant d, and this d is the delay, which is the same for all frequencies. And that's why we get a linear function. Yeah, and that means, or we can actually conclude from this property that the impulse response of linear phase filters have the property of being even symmetric about some center. Right? So this is actually how you can recognize a linear phase filter. So for instance, like this. Right? This is our example of our FIR design in the warp domain. But in the warp domain you can see it has symmetric coefficients. Right? So this would be a linear phase filter. So we have 4 samples, and we have a symmetry about the center d equals 1.5. Right? And it also turns out that this is the delay. Right? That we have a system delay of 1.5 samples, which means all the frequencies are delayed by 1.5 samples. So when you look at the picture here again, you can see here in the center, this is actually exactly the symmetry point. Right? This 1.5 samples here is the symmetry point, and this is also the delay, the resulting delay of this filter. So if you see an impulse response, a symmetric impulse response, you can conclude that it is linear phase first, and you can also see the center here is the delay for this linear phase. Right? All frequencies are delayed by this amount of samples. So actually you can get a lot of information just from looking at the impulse response. Yeah, here's another example for a linear phase filter. It's basically a piece of the sync function. So in IPython minus pylab, I just use those lines. So remember, you can easily start IPython pylab by going to, so you can look at the picture here again. You can see terminal. Let me do that here. So, I have Python minus pylab. So here I'm using Linux terminal shell, and here you go. Here we are now in the IPython interactive mode, and I can just copy and paste this line, or just type it hsync equals sync. So that's the sync function, the linspace, going from -2. So linspace creates numbers. These are the boundaries. So it creates numbers between -2 and 2. And it takes 11 numbers in this range. Right. Do you all know linspace? Okay. So actually I can take just this linspace part and plot it here. And then you can see we have simply numbers between -2 and +2, and we have 11 of them. Right? So 11 is just the number of numbers. So hsync is then just the sync function of those numbers. So here you can see the resulting numbers. So this is exactly what you can see here. So here's the sync function from those numbers. So it's basically a windowed sync function. So then we can plot it, and this is what we get. So here, it should look familiar to you. It's simply a sync function, the center of the sync function between -2 and 2. So this is -2, and this is +2. You just have a different x-axis because this is now denominating the samples. So it's not showing the x values, but it's showing the samples, the sample number. Yeah, and here you can see if you now interpret those coefficients as FIR filter, then we get a constant delay factor of d equals 5 because this is in the middle. Right. So when you look at those coefficients, here right in the middle, we have the 5. Right. We start counting with a 0 here. It's also important because this is 0 delay. And here we get 5 samples derived. Okay. So here we have a low-pass filter, which gives us 5 samples delay. Yeah, so the delay factor d is the center of the impulse response, and we can factor it out from the DTFT of the symmetric impulse response. So if we now apply the DTFT for the frequency response, remember we want to see that this is really a linear phase filter, then we get this equation. So here we have the coefficients. This is the DTFT, goes over the length of the filter. D is the center, so the delay, so that's why we have to go to 2D, because we have twice the length of the center. Yeah, so this is the usual DTFT. And then we can factor out the center exponential. So we have e to the minus j omega d. So here you can see it. So now we have to have factored it out. So same equation as here, just factoring out this e to the minus j omega d. And then we can see that this is symmetric around this d. Right? So half of the ends are below d and the other half is above d, because we have the symmetry. And this can be also used because this h of n is also symmetric around d. So the lower half is identical to the flipped upper half. So we just need the lower half of the sum, basically. So this is what you can see here. So here now I go only to half of it. Here we can see, let's see, d minus n, d minus n. So here is the minus. So this corresponds then to the upper half here. And we have those terms flipped, and this basically corresponds to the lower half, I guess. Sure. Not correct. So for the upper half, we have to flip d minus n, and then somehow we can come from here to here. So basically, this is the lower half, and then this is the upper half of our filter, because we have this symmetry. And then you can see that this term here is 2 times cosine omega d minus n. Using Euler's formula. Yeah, and this is a real number, right? So if you want to take the angle, the phase, all what's relevant is this term here. We have a complex number, the angle is given by this exponent, the magnitude is given by this expression here. But the phase is just the angle, so the angle of it is just this minus j omega d. So here, this minus d omega is the angle. And this is exactly the linear phase. So that shows that if we have a symmetric impulse response, we get a linear phase filter. Just from the symmetry. Yeah, so any symmetric filter has a linear phase. And the center sample corresponds to the sigma delta. Make sense?
Yes.
So this basically proves that a symmetric filter impulse response leads to a linear phase frequency response. Yeah, now we can also plot the zeros in the z-plane, so the zeros of our filters. So when we apply the z-transform, we get zeros. We have a z-transform, which is a polynomial, and this polynomial has zeros. And we can actually plot it in the complex plane of the z-transform. Let's say complex plane of the z-transform. Using our command z-plane. So z-plane is actually a function which you can find in Moodle 2. So that's our function. So you have to download it from Moodle 2. And then we can plot the zeros. So I can just copy and paste it here. Copy and paste. So you can see it works. Found z-plane. So that's good. So then I can just use this h-syn, which I just did. So I just need to have z-plane function. And this z-plane function is simply basically doing the plotting for us. Right here it takes the roots. So roots is a function from NumPy. It computes the roots of h-sync. Each sync taken as a polynomial. This is I think the pole location, and this is then the boundaries of our complex plane. So here's this plot here, and here you can see the result. Right. So here you can now see the location of the zeros. So each dot is the location of the zero. And here the green circle is the unit circle in the z-plane. So we can see here, we go from -1 to +1 here, this is the circle on the unit circle. Then we have zeros on the unit circle here, exactly on. Then one here in the center. And the most interesting pair is those. So one is close to 2 and one is close to 0.5. Can you see it?
Yes.
So this is actually characteristic for linear phase filters. Linear phase filters have zeros, which it turns out are conjugate around the distance from the origin. So this is around 0.5, this is around 2. So one is 1 over the other. Right? So they are reversed. Yeah, so this is the picture that we just saw. And when we look at the roots explicitly and apply the abs function, then we can see the distance from the origin. So this is what I did here. Abs roots. So we can do it here. Then we get the precise numbers, and you can see there's 1, 0 in infinity. Then there's one at, where's the one at 0? Here's the one at 0, right? So this also fits, one is 1 over the other. Then we have one at 1.9, and then we have one at 0.17, 0.517. So now we have to just check that this is 1 over this, to see if this really is the rule. Yeah, and indeed it turns out that this one number is 1 over the other number. Right? So it fits exactly. So we have this relationship that for each pair, for 2 zeros, we have 1 0 inside the unit circle at distance r, and 1 outside the unit circle at distance 1 over r. So this is the rule for the linear phase filters. So that might remind you a little bit of allpass filter, or simple allpass filter. Do you remember the relationship between the pole and the zeros? So we had a pole inside, and then there was a 0, 1 over r outside. Right? So you have the same effect here, just that this is now true zeros. Right? There's no pole involved here. Yeah, so here we have the effect that linear phase filters and filters have the property that their zeros are inside and outside the unit circle in the z domain. For stabilities, only poles need to be inside the unit circle, not the zeros. So that's why we can have zeros outside. But if we want to invert such a filter, for instance, for equalization purposes, the zeros turn into poles, and the zeros outside the unit circle turn into poles outside the unit circle, making the inverse filter unstable. Right? So this is now a problem. If you want to have an inverse filter, then the numerator turns into a denominator, and the zeros turn into poles, and all of a sudden the filter becomes unstable. So that means we cannot invert linear phase filters. And this might be a problem, for instance, if you want to equalize some amplifier. Yeah, so to avoid the instability of the inverse filter, we define minimum phase filters such that the inverse is also stable. Right? And that means all their zeros need to be inside the unit circle. So basically, the goal is to have the same magnitude response, but a stable filter, right? Different phases. Yeah, so we can write all linear filters as a concatenation of a minimum phase filter with an all-pass filter. So now we actually use this effect which I just mentioned. All-pass filters have poles inside the unit circle. Right? And now we can write this filter, this linear phase filter, as a minimum phase filter times an all-pass filter. So the all-pass filter already has zeros outside the unit circle, but poles inside the unit circle. So this minimum phase filter needs to have zeros inside the unit circle, outside the unit circle, to cancel those poles outside. So this can be seen from a hypothetical minimum phase filter, H-min, which has all its zeros inside the unit circle. Now we concatenate or multiply it with an all-pass filter such that its poles coincide with some of the zeros of the minimum phase filter inside the unit circle. These poles and zeros then cancel, and what's left is the zeros of the all-pass filter outside the unit circle at reverse conjugate positions 1 over A. So it's basically mirroring the zeros, the poles from outside to the inside. Yeah. Right, so in this way we can mirror out zeros from the inside, the unit circle, to the outside. The magnitude response does not change because we used an all pass with magnitude 1 for mirroring out the zeros. So as a result, we have a system with the same magnitude response, but now with zeros outside the unit circle. So now we know how to go from zeros inside the unit circle to zeros outside the unit circle, but still have the same magnitude. Right? We just mirror it from inside the unit circle to outside to get this different phases, but same magnitude. Now we can also go back. Right? We can use this linear phase filter and mirror from outside the unit circle to inside, and we know we will have the same magnitude, but now have different phases with minimum phase. Right. So assume we would like to equalize or compensate a given transfer function, for instance, from a recording, like a tape, for instance, maybe an old tape, and we want to equalize it. As we saw above, this transfer function can be written as the product h equals h min times h all pass. Only the h min has a stable inverse, hence we design or compensate, we design our compensation filter as 1 over h min. So this is now which we can compensate. And we can obtain a minimum phase version of our transfer function h min and then use it as an equalization filter. So if we apply this compensation filter after our given transfer function, for instance from a recording, we obtain the overall system as G is h of z from our system times the compensation filter, and what's left is the all pass. So we cancelled the minimum phase part, but what's left is the all pass filter. Yeah, this means the overall transfer function is now an all pass with a constant magnitude response and only phase changes. And you can also read more about it in the book by Oppenheim-Schäfer, Discrete Time Signal Processing. Yeah, so the question is, how do we obtain a minimum phase version from a given filter? Right. Well, basically, we mirror in the zeros from outside the unit circle. We take the above example of the piece of the sinc function in our Python example here. Right. So when we look at our sinc function, we have the roots. So we can take the roots function. So here we took the abs function, we can just remove the abs function, and then we see the location. And this is what we can see here. Right. So now we can see the complex location of each zero that we have here. So real and imaginary part. Right. And then we just have to look for the zeros outside. So there's a 0 at 1.93. So where is it here? So here you can see the 0 and 1.93 on the real axis because it has 0 imaginary part. Right, so this is clearly outside the unit circle. So now we have to mirror it in. we also neglect the 0 at infinity, which comes from starting with a 0 sample. So this is actually an artifact of taking my sink example, because the sink happened to start with a 0. Yeah. So to achieve this, we first take the z-domain polynomial of the impulse response and then cancel the 0 outside by dividing by the polynomial which has only that 0. So here you can see a polynomial which has only this outside 0. Right? So you can see it if z is equal to 1.93, then we have 1 minus 1 is 0. So we have a polynomial which has a 0 at this point. Right? So if we have a polynomial which has a 0 at this point, and we divide it by this small polynomial, then we put a pole at the location of the 0 and it cancels. Right? So the result polynomial should have no remainder, and it should have a shorter polynomial which doesn't have this outside 0. Make sense? So this is what I do here. I use the function SciPy signal processing, SciPy signal, to divide polynomials, and that's done with the function deconvolve. Right? Again, deconvolution is polynomial division in the z-domain, and that's why it's called deconvolve. So we are using our h-sink, which is this polynomial of our z-transform of our sink function, or rather we just interpret it as a polynomial. It's just the coefficients here. h-sink are the coefficients. And here are the coefficients of our short polynomial, which has as a 0 only the outside 0. So you have this divided by this. And after this polynomial division, we have a result polynomial in B, and R is the remainder. And this is also a good test because the remainder should be 0. Right? Because if it really perfectly cancels, there should be no remainder. If there's a remainder, something went wrong. Right? Then there's a bug. So here you can see the result polynomial. So far so good, doesn't say much. Here is the remainder, so we have to check that the remainder is really 0. Yeah, is it 0? What do you think? No? Yes? Who is for 0? Who is for not 0? Yeah, in a certain way you're both right? Because there are clearly non-zero entries here, right? But when you look at the exponent, 10 to the minus 17, right? So this is basically rounding errors. Again, Python has an accuracy of about 10 to the minus 16 roughly. So this is clearly rounding errors. So for Python this means 0. Right? So up to numerical rounding errors. So this is also something you always need to keep in mind when you work with numerics. A 0 doesn't always look like a 0. Right? It can be a tiny number. Yeah, so this is good enough for us. So the R is practically 0. So it passes our test. So we can indeed divide our polynomial without any remainder. Yeah, so after that we can multiply the obtained polynomial b with a 0 inside the unit circle at position 1 divided by 1.93. Right, so now we do the mirroring in. So first we remove the outside 0, and now we add the inside 0. By multiplying it with a polynomial with only that 0. So here you can see this is the polynomial which contains the 0 inside the unit circle at position 1 divided by 1.93. So now instead of division we have multiplication, And polynomial multiplication is done with a convolve function, so we convolve the coefficients. And here you can see it, so we have b, our result polynomial, and multiply it with this short polynomial. And yeah, the conjugate doesn't really apply here because we have a real value. But if this would be a complex value, we don't need to have this conjugate complex. We need to avoid this flipping to the other side of the avoid sign changing the imaginary part. Yeah, and here is now the result. So here we don't have remainder because we do the multiplication. Here we can see the resulting polynomial. So again, it starts with a 0. This is this artifact from the sinc function, which is fine. So this is now our minimum phase version. And now we can check it out. Right? So those numbers don't say us too much yet. So we have to plot it and compare the frequency response in magnitude and phase. So first, I plot the impulse response. Right. So here you can see it. H sinc minimum phase. And this is now the impulse response. You can see it looks quite different, right? It's no longer symmetric. The symmetry is gone. Remember, the symmetry was around 5, right? But no, there's no symmetry here. And it has the first peak. Remember here, the zeros is up here, right? So the first large entry is now at sample number 3. So you could argue that you get now a signal delay of about 3 samples, but keep in mind that different frequency is different shifts. So now we don't really have the exact delay because it depends on frequency. So you have this first main lobe coming first, and then we have a side lobe coming later. So actually 2 side lobes here. So this is also characteristic of a minimum phase filter. You have the main lobe without a beginning side lobe. So first comes the main lobe, and then you have wiggles behind it. So that's interesting. So it's non-symmetric, and we have the peak at the beginning of the impulse response. Now the interesting part, the most interesting part is actually the frequency response. So for the frequency response, what do we want to see for the frequency response? We want to have the same magnitude, right? The magnitude should be identical to the linear phase design, because that was what we needed for our equalization. Right? So here's now our frequency response. And here you can see the phase, and you can see it's a little bit round here, right? Can you see it? So it's not exactly a straight line, it's a little bit bent. Although not much. Right? So this is a nonlinear filter, but only slightly nonlinear. So it's actually not that bad. So you can see here, when you look at the gradient, the derivative at different points, you will see slight differences, which means frequencies here at the low end are slightly differently delayed than higher frequencies, but not so much. So that's also good. And now we compare it with the linear phase version. So here I'm now using frequency of H sinc. And this is what we get. So here we can see that the magnitude is actually exactly the same. But the phase is now much different. So the phase is really straight, and it also is much more steep when you look at it, right? It has a much steeper shape. So going back to our minimum phase version, here it took much longer time before it reached the wraparound point at pi, or roughly pi. much less steep, which means it has much less delay. So this is actually another big advantage, that this filter gives you much less delay than the linear phase version. So not only does it have the same magnitude response, but it also gives you less delay. So this less delay is important in real-time applications. For instance, if you have somebody on the telephone or using teleconferencing, you don't want the speech to be delayed too much by the filtering degree on the way. So here you have such a version. You have a good magnitude response, so this still works nicely as a low-pass filter, the same low-pass filter as before, but it has much less delay than the linear phase version. And the slight non-linearity usually doesn't really matter. Right? The big advantage here is the low delay. Yeah, so we see that it's having an identical magnitude response, except for an offset of about 5 dB, which doesn't really matter because you can always compensate it by a constant gain factor. And looking at the phase, we see that the minimum phase version has less phase lag or group delay. -7 radians at frequency 1.5, whereas the minimum phase filter has a reduced phase lag of about 5 radians at this frequency. So let's check the normalized frequency 1.5. So here's 1.5 for the minimum phase version. So 1.5 is about -2 radians at this point. Can you see it? So now we go to the linear phase version, 1.5. So now we actually have to check the wrap, we have to count the wrap around. So this is -1 point something, and here we have -3, it goes up, -pi, then it goes up to pi. So actually this is then -1 point something minus 2 pi. So 2 pi is 6. -6 minus 1 is actually -7 something. Make sense? So including wraparound, we are around about at -7, a little bit more. And in the minimum phase, we just have 5. So we have a correspondingly lower delay. Yeah, so if we take the derivative of the phase function to obtain the group delay, we will get correspondingly lower values, which means the minimum phase filter will have less group delay than the linear phase filter. In fact, it has the lowest possible delay for a given magnitude response. Right? Because all the zeros are now inside the unit circle. And that's basically all we can do. Right? So if you have a given magnitude filter design and want to obtain the lowest possible delay, you have to take minimum phase filters. And you can design them in the way I just showed you. You start with a linear phase design, for instance using REMIS, and then convert this to a minimum phase design in the way we just did, by mirroring in the zeros. Yeah, and a convenient SciPy function to obtain a minimum phase filter with a similar, not exactly the same magnitude frequency response of a linear filter is SciPy signal minimum phase. So this is also kind of an interesting function that basically is doing those two steps that we just did, REMIS and mirroring in the zeros, but it uses a somewhat different algorithm. And that's also why it expects a filter with a squared desired frequency response. Right. So it's kind of tricky. So here in IPython we can type, for instance, help sp minimum phase. And try that. Of course, I have to import SciPy sigma as sp. So this is where the library is. And here we get the help function. So we have h. This is the linear phase filter. So this comes out of, for instance, premise, but needs to be squared. And then we can provide a method and the number of FFT bits used. Number of points for the FFT. And returns the minimum phase filter. Yeah, and this squared frequency response can be obtained by convolving the linear phase filter coefficients with itself. Right. Basically, convolving in the time domain is squaring in the frequency domain. Remember? Convolution is multiplication in frequency domain. Yeah, in our example, an approximate linear filter is obtained in IPython using, here we use hsync again. And I'm not sure if I did the import. So maybe I should add it here. Import signal as sp. So here I can now compute it in my IPython shell. Yeah. So you can see here the first step is to convolve our hsync filter with itself, the linear phase filter. In our case, it's this piece of the sync function, but in general, you would use premise to obtain a filter, for instance. Then convolve it with itself, then apply this function minimum phase to it, to the squared version, and then you get the minimum phase version. And let's see what we get. Frac of hmin. Frac of hmin. Oh, import. Let's see, import star. Yes. So what do you think? Is the same that we just saw? Not exactly, right? Particularly here, the phase looks kind of funny, right? Yeah, and this is basically all they promise with their function. It's similar, but it's not exactly the same. So the magnitude is actually quite good. So when we look at the magnitude and compare it, yeah, it's pretty much the same, right? We get about, I guess, 30 dB here as stop attenuation, and in our case, we have the same. So we have about here from 10 minus 10, maybe roughly the same. Did you have a question?
Sir,
yeah.
Can you explain why the phase is behaving like this? I can understand the first step in this graph also.
Yeah. You mean this?
It is because of minus pi to pi it is changing, but then the next step it is like minus 2 radians. Yeah. So at around 0 radians and at minus 2 radians suddenly it is jumping to 0 radians.
You mean here?
Yes.
Yeah, it's not exactly minus pi, right?
No, minus pi is minus 3.14, but
Yeah.
if it is around minus pi, I can understand that it is wrapping in the modular, but why it is behaving like this?
Yeah, I mean like jumping around here.
Yes.
Yeah, it's strange. Don't know. It's indeed strange. It shouldn't do that. So maybe it's some numerical artifact. I don't know. So this here, this is what you would expect, right? You have minus pi and you have pi.
Yes.
Right? But then here it's doing the same stuff. An explanation actually might be that when you look at the positions where it's doing those jumps in the magnitude. Yes.
Okay.
So this is basically where the magnitude becomes 0. Right? So you get tiny numbers, and that also means those numbers for the phase, they're kind of questionable, because what's the phase of 0?
Yes.
Right? So that's why basically when you have this magnitude 0, basically the phase in this area is kind of questionable.
But if we say that at the point where it is 0, the magnitude is 0, that phase is behaving like in one way in the left hand side and another way in the right hand side.
Right. Exactly. So let's take a look at the minimum phase version. Yeah. So here you had the same thing, right? You had this behavior at the 0 crossing of the magnitude.
I got it. Thank you, sir.
No. Okay. Yeah. Good question. Right, so here we have our minimum phase filter. Put that upload because I don't see a figure here. Interesting. So maybe I should add this import. Let's see, import star, and then we can plot it. And we get this kind of funny picture here. What is it? Yeah, so here you can also see this jump here now appears at minus pi and plus pi, right? Which somehow it didn't do before, right? When you compare it with the linear phase version. Linear phase is here. Yeah. And that's because here it started at plus pi, and here in the figure it starts with 0. Right? Can you see that? Here it starts with phase 0, and here it starts with phase pi. What's the difference? Right, but what's the difference between 0 and pi?
It's half sample difference.
Well, basically it's switching the sign, right?
Yeah.
So you go from +1 to -1. And this again, this is basically a factor, right? And factors don't really matter for filtering, because you can always compensate factors by just multiplying or dividing by them. So this is again an artifact from this design, right? So this design gives us an opposite sign, and that's why we get this wraparound at this position here, and not here. So this is again an artifact. And that's also why it looks so different. What's also kind of funny here is this little peak here. But again, it also appears at a 0 crossing of the magnitude. So again, it's kind of like an artifact here. numerical problems because of disappearing values. Yeah, since I have it here now, we can also plot the values. So H min is this, and you can compare it with previous H min, which was H sync minimum phase. H sync minimum phase.